With regards to numerical fractions, we will begin with multiplication and division, ahead of addition and subtraction, which is more complicated. But before we introduce them, I want to talk about prime numbers. Remember that phrase, prime numbers. Below, I have listed the natural numbers up to 20. The first three natural numbers have no factors. 4 has the factor 2 times 2. 5 has no factor except 1 and 5, but these don't count. 6 has the factor 2 times 3. 7 doesn't have a factor. 8 is 4 times 2, or 2 times 2 times 2. 9 is 3 times 3. 10 is 2 times 5. 11, none. 12 is 4 times 3, or 2 times 2 times 3, or even 2 times 6. 13 doesn't have any. 14 is 2 times 7. 15, 3 times 5. 16, 4 2s in a row. 17, none. 18, 2 times 3 times 3. 19, none. 20 is 2 times 2 times 5, and so on. On this page, check the list where you see no factors. This number is called a prime number. Number 1 is not counted in the list of prime numbers. So the lowest prime number is the number 2, which is an even number. The prime numbers, as you can see where it says no factors, are 2, 3, 5, 7, 11, 13, 17, 19, and the list goes on, like 23, 29, 31, and so on. Theory tells us that there exists an infinite list of such counting prime numbers. The other numbers in the lists are factored into their prime numbers. You see, I've used the word prime again. Thus, 4 is equal to 2 times 2. But 8 is equal to 4 times 2, but 4 is not a prime. So we would list 8 as equaling 2 times 2 times 2, the prime numbers. All other numbers in the prime number list are odd numbers. The number 2 is the only even prime number, and all the rest are odd. Odd numbers are not divisible by 2. Remember these words and what they mean: factors and products. Well, what is a fraction? Most people know what a fraction is. People use them every day. People speak about a half of this, 3/4 of that, 5/8 of something else, and so on. An ordinary fraction, remember this phrase, ordinary fraction. An ordinary fraction is a number made up of 2 parts. In my example, you see there, we have A and B, where A is written over B with a line separating them, such as in A over B. So A over B is the ordinary fraction. The line separating the two numbers sometimes can be called a bar bracket. You have seen this expression before in an earlier lecture. We used words like A was called the dividend. B, which is in the bottom, was called the divisor. And the entire amount put together is an indicated quotient. So an indicated quotient is the fraction that we are describing here. When working with fractions, here are some words that you must remember. The part on top, A, is called a numerator, And the part on the bottom, b, is called the denominator. We now introduce some new vocabulary. A proper fraction is an ordinary fraction. This is a fraction with a numerator smaller than the denominator. So the top number is smaller than the denominator when it is a proper fraction. Such a fraction is always less than 1. Next, we have improper fractions. An improper fraction is an ordinary fraction, and this is where the numerator is greater than the denominator. Such a fraction is always greater than 1. Therefore, examples of improper fractions are 4 over 3, 3 over 2, 12 over 7. Another term to add to your mathematics vocabulary is the phrase mixed number. The improper fraction can and is often written as a mixed number, or you can call it a mixed fraction. That is when the numerator is larger than the denominator. I will show you how to use the calculator to change an improper fraction to a mixed number later. We are going to use the pencil and paper method, and it goes as follows. Lay out the problem as you can see in the bottom with the divided by sign. And so we would refer to this as long division. From 5/3, the result becomes the divisor 3 in the denominator is divided into the dividend 5, which is in the numerator, and the result is 1 in the quotient. Now, multiply 3 times 1, and that is equal to 3, which is written under the 5. Subtract, and 2 is the remainder. 1 is in the quotient, and with 2 in the remainder, you would write 1 2/3. Technically, 1 2/3 means 1 plus 2/3. I will now show you how to use your calculator to do the same problem. Divide the 5 by 3, and you get on your display 1.666 and so on. Use continuous calculation. Subtract from the display the number 1 so that you have left 0.666 and so on. With this 0.666 and so on left over, multiply this number by 3. And when you multiply it by 3, you get the remainder 2. And this becomes your fraction 1 2/3. Although 1 2/3 is a convenient way to rewrite improper fractions for better understanding, if further calculations are required with the number, the mixed number is not in its practical form. Most work with fractions will not be as mixed fractions. Here are some examples. 3/2 is equal to 1 1/2. 24 over 7 is equal to 3 3/7. 3,567 over 42 is 84 39 over 40. Mixed numbers are neat and effective ways to interpret improper fractions because you get a clearer idea of how such amounts to, but as I explained earlier, the mixed number is not a useful form when more arithmetic is necessary. This is especially true when mixed numbers must be multiplied or divided. Because operations are often applied to an extended expression of mixed numbers, and because simplifying expressions of this type is often difficult, it is best to change the mixed number back to improper fractions. A slick and efficient way to change a mixed number back to an improper fraction will now be described. Let's take 8 3/5 as an example. Take 5 multiplied by 8 and add 3. 5 times 8 is 40, and 3 is 43. Now write the result over 5, and you get the improper fraction 43 over 5. Notice how the multiplication and addition is performed in a circular way. At the bottom you can see that I have 5 with an arrow and a multiplication sign, and another arrow to 8, and then an arrow with a plus sign and 3. So we go into a circle. 5 times 8 plus 3 is 40. 3, which when put over 5, gives you the improper fraction 43 over 5. Similarly at the top, where we have 3 halves, 2 times 1 is 2 plus 1 is 3 over 2. Next, 3 times 7 is 21 plus 3 is 24, and that's 24 over 7. We will now apply the basic operations of arithmetic, add, subtract, multiply, divide, to these fractions. By acquiring skill in working with numerical fractions will help you later when you apply these skills to algebra. As I said at the beginning of the chapter, we will apply multiplication and division first because it is the easier application. Reading from the top, if you will, we want to emphasize a not so trivial concept. That is, 1 over 1 is equal to 2 over 2 equals 10 over 10, 725 over 725, 3 plus 1 divided by 1 plus 3, which is 4 over 4, are all equal to 1. Therefore, we would have 7 times 2 over 2 is the same as 7 times 1, which is equal to 7. If you drop equal factors from the top and bottom before simplifying, this is better than multiplying first and simplifying later. What you don't want to do, as you see in the example, multiply 7 times 2 equals 14 and 1 times 2 is equal to 2 before you simplify to get 7. What you want to do is to cancel out the 2 and 2 so that what is actually left is the number 7. In this example with regards to multiplication, we have in the first one that 1/2 times 1/3 is equal to 1 times 1 across the top and 2 times 3 across the bottom, which is equal to 1/6. In this next example, we have 5/8 times 7 over 2 times 3 over 6 times 8 over 9. Across the top, we have 5 times 7 times 3 times 8. And along the bottom, we have 8 times 2 times 6 times 9. You can see we have a very large fraction, 840 divided by 864. Before we do all that multiplying across the top and bottom to get 840 over 864, we should look to see if any factors on top match those that are on the bottom. Matching factors equal 1 and can be dropped. You can see we have factored all numbers into primes, and by removing matching pairs, we ended up with 5 times 7 on top, which equals 35, and 36 on the bottom, resulting in the reduced fraction 35 over 36. The word reduced is important here. We also call it simplified, and the process of doing so is simplifying. You will often be expected to do work where fractions have to be simplified. In this example, there are shortcuts to the process. For example, instead of reducing everything into primes, we can cut out equal numbers. For example, we can see that 8 is over 8, so we can drop that, and it won't be necessary to break them down into primes. Also, there's a 3 that matches a similar factor 3 in the number 6 at the bottom of the fraction, which will reduce a lot of your work. In the next example, we have 15 over 24 multiplied by the fraction 8 over 10. The result is, across the top, 15 times 8, and across the bottom is 24 times 10. If you factor these into primes, you can see we can pair off quite a few of the numbers in the numerator with the same number in the denominator. If you pair these off, you end up with 3 over 3 times 5 over 5, and so on and so forth, and you end up with 1 times 1 times 1, and the entire fraction is equal to 1/2. Every time there's a number on top called the numerator, which matches with a number on the bottom called the denominator, these must be dropped off into pairs before finally multiplying to get your final answer. This process is sometimes called canceling in pairs. Remember that phrase. In this next example, at the top of the page, we will use the word cancel. Look at the fraction. Since 28 is equal to 2 times 2 times 7, and 24 is equal to 2 times 17, we can cancel pairs of 2's by putting strokes through them. We can put a 1 next to them if you want, but it's not really required. In the next 2 screen pages, we study the simplification of the division of fractions. That second example you see on the page is 1/2 divided by 3/4 and is referred to as a complex fractions. And our goal is to change it to an ordinary fraction. This is a case where you have the fraction 1/2 over another fraction 3/4. We change the division problem into a multiplication problem by replacing the divided by operation to a multiply by operation, followed by reciprocating the second fraction from 3/4 to 4/3. So we write 1/2 times 4/3 is equal to 4 over 6, which is equal to 2/3. A second example of a complex fraction at the top of this page is the fraction 4/15 divided by 8 over 35. And what we do with this fraction is to change the divided by sign to a multiplication sign and reciprocate the 8/35 to make it 35 over 8. So we've changed the problem into 4 divided by 15 times 35 divided by 8. Now 4 will cancel 8 and make it 2. In 15 we can divide it by 5 to change it to 3, and 35 divided by 5 will change that to 7. And the result will be 1 times 7 equals 7. 3 times 2 equals 6, and we end up with the ordinary fraction 7/6 as required. When we are dealing with integers in the numerator and denominator, The negative sign can confuse matters. There are three places where negative signs may occur, actually: in the numerator, in the denominator, and in front of the fraction itself. Remember that when simplifying integers, when you're multiplying, that an even number of negative signs can be replaced by a single positive sign, and an odd number of negative signs can be replaced by a single negative sign. Now this is important. Never leave a fraction with a negative sign in the denominator when you're simplifying. In my example, where I'm using 3/4, you can see that there are like 6 possibilities of signs occurring in different parts of the fraction. You can have, for example, -3 over +4. Or you can have -3 over -4, +3 over -4, or -3 over -4. And we have minus -3 over +4, or +3 over -4. What we need to do when we write this fraction in its final form, to have it represented by only one sign. In my example where I use 3/4, you can see that I have a negative sign in the numerator, -3 over 4, and that is equal to the decimal value of -0.75. Now the other place that we can put that negative sign in this fraction 3/4 is level with the line separating 3 and 4, as you see in the example. Other placements of positive and negative signs are illustrated in the last examples of the page. Here are 3 examples at the top of the page for the student to try. The answers to the first one is 5/16, the second one is 2/15, and the third one is -12 over 49. We now examine the final 2 operations which involve adding and subtracting of fractions. This process has a lot of parts to it and is done last. What we must emphasize right now is that you cannot add fractions with different denominators until, with necessary work, you change fractions so that they do have the same denominator. And you can see what I mean by looking at the bottom of the page, that if you have a half plus a half, we can add these to equal 1, because the denominators are the same, which in this case equals 2. Let us have a look at our simple example where the denominators are different. Check that example where I'm asking you to add 1/2 and 1/3. If you change the fractions into decimals, 1/2 is 0.5 and 1/3 is 0.333 forever. So when you add the two, 1/2 plus 1/3 is equal to 0.8333, etc. Now, carefully study the list of equivalent fractions which I have listed. 1/2 is equal to 2/4, equals 3/6, equals 4/8, and so on, all the way up to my list, which ends at 9/18. But as you know, this list can go on forever. Next, I have 1/3, and that list gives you 2/6, 3/9, 4/12, 5/15, and so on as well. Now, here is the thing. Check off carefully how many fractions do you see where the denominators are the same. 3/6 is the same denominator as 2/6. 6/12 has the same denominator as 4/12. 9/18 is the same denominator as 6/18, and that list can go on forever. They all can be added when the denominators are the same. But what our objective is to find the pairs with the smallest denominator. And 3/6 plus 2/6 wins. If you add these up, you get 5/6, and that is the exact representation of a half plus 1/3. Now, to be able to do this requires a bit of preparation. So now we have to learn a direct way to find the common or equal denominator without having to prepare lists of equal fractions, and that will take a little bit of preparation. What you must do is find what we call the LCD, the lowest common denominator.